This plastic bottle, it'll outlive you, your parents, your grandparents, and probably a few more generations after that. Plastic can last for centuries before it breaks down. That means every bottle you've ever used is probably still around, piling up in landfills, floating in oceans, and breaking into microplastics that we can end up consuming. Polyethylene terephthalate, or PET, is one of the most common plastics on Earth. PET is everywhere. If you ever used a bottle or worn polyester clothes, you've encountered PET. On paper, it looks degradable. Its chains are held together by ester bonds that water and enzymes can't break. But here's the catch. PET is hydrophobic and packs into tight crystals, so those bonds are hard to reach. In 2016, Japanese scientists found a bacterium that could survive on PET as its only food source. That bacterium was Ideanella psychiensis. Don't worry about the name. What matters is that it uses a special enzyme called PETASE. Let's imagine PET as a whole apple, and dealing with it is a bit like giving an apple to a baby. Just like how a baby can't really do much with a whole apple, bacteria can't do much with PET. That's where PETase and another enzyme, metase, comes in. Through a process called hydrolysis to break the ester bonds, PETase slices it into pieces called met. But babies can't do much with apple slices too, right? And bacteria can't do much with met either. That's where metase comes in. Like mushing apple slices into applesauce, it turns met into two simple building blocks, terephthalic acid and ethylene glycol. And that is finally small enough for bacteria to digest. Now here's what makes PETase special. It looks like a lot like another enzyme called cutinase, which breaks down the natural plant polyester. The key difference is that PETase has a wider groove, more like a scoop that grips on PET's bulky chains and cut bonds other enzymes can't. Scientists thought this wider groove was an evolutionary adaptation for PETase. However, one mutation, which narrowed the groove, actually boosted activity. That told us two things. First, our understanding of how structure affects function is still limited. And second, if a single mutation can help by accident, imagine what we can do on purpose. If we engineer PETase to be faster and tougher, it could chew through plastic at an industrial scale. So maybe the solution to plastic pollution isn't some giant futuristic machine, but a microscopic enzyme with a scoop, turning our plastic problem into a recycling solution.